Hey everyone, this talk is called Lighter Than Air. We're going to look at consensus layer light clients of the Ethereum network. So first, a little bit about me. I'm Alex Stokes. I do research and development at the Ethereum Foundation. Lately, I've been focused on the Altair beacon chain upgrade, which we'll hear more about in the rest of this talk, and also security and testing of the different beacon chain client implementations. If you want to reach out to me directly, Twitter is probably the best way to do that. There's my handle, ralexstokes. Please reach out with whatever you have. So in this talk, hopefully we can answer these questions. What are light clients in the first place? How do they work with Ethereum's consensus layer? And why should you care? And you may ask that last one because you come to the space and you hear all these things like thrown at you suddenly. There's like mining nodes or validating nodes, full nodes, light nodes, even things like stateless nodes. And it can be really confusing. The point is that we have this shared data with the blockchain, and it turns out, there's a huge design space, all these trade-offs we can make in terms of how we access that data. And for light clients in particular, right, we can actually trade off security for the resource consumption of processing the chain. So we'll start with some history. This goes all the way back to the Bitcoin white paper with simplified payment verification. The basic idea, and this is the general design of all proof of work light clients, is you just keep track of the headers. So the headers are summaries of the transactions in the block, so they're much smaller than the full block. So again, as a light client, you have much less to download. And if you need to make any queries about the state of the blocks or the chain at that point, at a given point in time, there's some way to do that, maybe with Merkle proofs or something like this. We've had for a while, right? We've had LES and our dev P2P networking stack in Ethereum. And yeah, it works today. You can go run an LES client, both client or server. And yeah, just to round out some of the intuition, as a light client, right, you only have the block headers. As a light client, you basically are following the header, the chain of headers with the most work. So each of these headers commits to a difficulty, which gives you some sense of how much hash power went in to sort of steal the block and let a miner append to the chain. They also commit to a Merkle root, right? So by following the longest chain, we know what the canonical one is. And then by using this Merkle root, we can then ask trustlessly, for example, was my transaction included in this block? And we have something called a Merkle proof that lets us do this with not too much overhead. We can know yes or no based on the data I trust in the header I receive, if a transaction was there or not. And in Ethereum, this generalizes right to the full state, and you can have all sorts of sophisticated queries. Cool stuff. So then, yeah, we can ask about the security model, right? So we're only tracking the chain of headers, and for light client, it's great because it's way less to process. However, we're now reliant on a majority of the hash power to be honest. And what that means here, right, is that if there is, if the set of miners in Bitcoin, for example, is corrupted, then they could append some malicious block to the chain and not show us another block, or even just only give us the malicious block. And as a light client, we wouldn't actually know. So in order for this to be sound, we need to require that a majority of these miners are honest. Otherwise, they could do things like this. This is a pretty classic attack. So as a miner, I go along, let's say I make this malicious block, the first one, I add it to the chain, and I just make a fake transaction that gives me 21 million Bitcoins on top of however many coins there already are. As a light client, this is all I see. And so I wouldn't actually know that this malicious transaction was included, which is actually quite bad. So that's why you do have this very strong requirement that the majority of whoever's giving you this consensus data is honest. But again, it's a trade-off because now, as long as you can assume that, then you now don't need to bother with a bunch of transaction data. So, right, you don't get anything for free, but if you're making smaller day-to-day transactions, then this actually could be plenty of security. And again, this is the trade-off you're making. I'm sure you've heard of this by now, right? We have a very celebrated move to proof of stake on the way. We launched the Beacon chain. It's driven by a proof of stake consensus instead of a proof of work consensus. And it aims to be a more secure, scalable, and sustainable home for Ethereum. I took this snapshot here from the website Beacon Chain, and it has some stats on the Beacon Chain right now. So you can see we have epochs and slots, which are units of time. So it's been going for a while. This is pretty cool, right? Over 200,000 active validators. So a lot. I believe that's actually orders of magnitude more than any other proof of stake network at the moment. Almost 7 million, more than 7 million staked ether. It's pretty incredible. And now, the design changes a bit because we don't have this proof of work header chain to rely on anymore. We can still have a header chain, but there's no hash power or difficulty that we can use to figure out what the canonical chain is. So instead, we're going to rely on the validators and then require validators to make cryptographic signatures on this canonical chain. So they just sign, the chain every so often, even as often as every block. And then as light clients, we consume that and we say, oh, this is the chain because it's the chain with the most stake that I've seen rather than the most work. But okay, so we take this like very naive design and we kind of already run into a problem because in Ethereum we strive for a very broad decentralized ecosystem, and this is a great strength. But one way we realize this is we have a very large validator set for the beacon chain, right? It was over 200,000 validators. So that kind of is confusing, right? If we wanted to design a light client, because we just said we want the whole set to sign off on the whole chain. So you have, over 200,000 signatures every block, like that actually sounds quite heavy. So what are we going to do? And it turns out we have this pretty cool technique that we use in many places all over the beacon chain. But the idea is rather than having the whole validator set, we're going to have subsets. And we call these subsets a committee, right? So you randomly sample different subsets of the validator set. And so I tried to model this here. There's like all the validators represented with this like blue-gray circle. Then we have like random subsets in like the purple, green, and orange. And for the sync committees, which are these committees we're going to use to facilitate the light clients, what they're going to do is rotate every day. And they're still going to sign off on each block, but they're going to do it, well, it'll happen in a way that is much smaller for light clients because it's a much smaller set of validators. So let me explain the picture here so it makes more sense. The blocks here are at the bottom, so this is representing the chain, and then the line here with like the vertical marks, that's representing time. So then it's like every day we're going to have a different random subset of validators perform this duty to sign off on the chain, right? So you have this purple committee, move to the green committee, move to the orange committee. And that's going to be sort of our core primitive here is we make this sync committee that is randomly called from the full set. They're going to serve for about a day of signing the chain. And those signatures are what end up going to light clients. Light clients accept a majority of these signatures in order to know what the canonical chain is at a given point in time. And we still have this honest majority assumption. And so, our task now is to make sure that it's really hard to corrupt the sync committee. And there's a number of ways we do this, right? So first off, there's just a huge validator set. Like I said before, over 200,000 validators, and that number is just getting bigger. So first off, there's just many validators to pick from, and hopefully the more there are, the less coordinated they are. The way this shuffling works is that it's driven by randomness on chain, and you only have maybe a day or less of look ahead, right? So what that means is that basically you might not even know until it's too late for you to pull off an attack who you need to even target in the attack. And then, yeah, along with that, right, we have the frequent rotation where, again, this period is only like a day. So even if you do know the committee and they come to serve their term, so to speak, you only have so much time to actually like coordinate them. And if it's this like large randomly sampled set, like it becomes quite hard to imagine how you even like start doing that. The committees let us do other cool things. So for example, they facilitate sync and like actually quite efficient sync. So the way this works is that not only are each committee going to sign off on a block, they're also going to sign off on the next committee. And so what that means is we actually only kind of need one update per period to know, hey, the state of the chain was this, and also the next committee was this. And because we know that, we can actually use that to skip committee to, we can use that to skip from committee to committee. Stumbling over that one. I don't know if it's called this, but just to give you some intuition, we'll call it skip sync. And the idea is rather than having to go block by block and say, okay, figure out who the purple committee is, get all of their signatures, and then for each block, figure out the block, and then move forward. We can just go once per period. And so I put these gold blocks here to like, highlight that. All I need to do when I'm syncing is, even starting from Genesis, I only have to go one block per period, because one update, will give me the block. It will also tell me who the next committee is. And so that way I can skip forward period to period. And then I can do this all the way up until like the current period, say the orange committee is in the current period, where then I can say, okay, now I go block by block. So it's a really efficient sync, than a more naive method where you do have to go, through all the blocks. And if you sync to full node on Ethereum, you know that it can actually take quite a while. So this is pretty cool. To give you a sense how this all ties together, because not only do we want to know the head of the chain, we actually want to know the state of the chain, right? And so these light client updates I was talking about, right? So if you go period by period, you go gold block to gold block, you get these updates, which are headers of those gold blocks. The headers have been signed, so you know they're valid. The headers then contain a state root to the beacon state, which is the state of the beacon chain. This state root, then you can authenticate to a particular beacon state with Merkle proofs, like we could with the SPV setup. After the merge, the beacon state will contain an execution payload header, which again is the header we know from Ethereum today. That header contains a state root. This is the Ethereum state that we all know and love. Has things like token balances, NFT auction state, Uniswap pools, all of that fun stuff. So the point being, as a light client, you can have a really efficient sync to get to the head of the chain. You can then, via this whole tower of Merkle proofs, ask really precise things about the state of the network, and get it sort of authenticated right in this like very trustless fashion. So, and that unlocks a lot of use cases, like even today, right? The obvious one, right, is like having an Ethereum client on your phone or in your browser. Rather than having MetaMask reach out to Infura, MetaMask can like wrap a light client, which then is reaching out to this decentralized network. It also facilitates trustless bridges. So basically all of the bridge designs that you hear about, this is how they work, is, chain A wants to talk to chain B, then, it's a light client of the other chain and vice versa. So, if you want to bridge Solana or Avalanche or whatever other chains are out there these days, right, you can, you basically want to have a light client of the beacon chain to bridge to the Ethereum network. This work also, is a really exciting foundation for tomorrow. In the same way that we talked about like authenticating data with all these Merkle roots, we could imagine similarly authenticating computation. So I could even say like, hey, I'm a light client. I want to know, some token route to make like a trade on Uniswap to SushiSwap back. And, for some reason I want someone to do that for me. So then I could actually say, hey, here are the inputs. Here's like a chunk of WebAssembly code I want you to execute the inputs against. You get an output, and you could even get back some authentication that here's the output and also the computation was done correctly. And of course, this can be extended. You can compress that verification with snarks and techniques like that. It also serves as foundation for what I'd say is the broader vision of Web3, right? Where these networks are permissionless. That permissionlessness leads to innovation. The innovation then leads to like hopefully greater opportunity for everyone. What that looks like is your light client can like trustlessly request a decentralized front end, for example, like OpenSea on IPFS. The light client itself serves as like your Web3 endpoint as a decentralized backend. And suddenly you don't have this reliance on, platforms that may censor you or, choose to try and control your behavior in other ways. So hopefully that piqued your interest. You're like, cool, I want to get involved. What can I do? And there's a ton. So on the research side, there's plenty of specifications and like work we can do to improve that there. There's an issue even on the specs repo you can check out. There's this pretty cool design with Cello called the ultralight client, where basically you make a snark for those light client, those committee jumps. So that's worth looking into. Also, there's this whole question of incentivizing the light server. So we didn't talk too much about that, but that's, I'd say, a problem with LES today is that there just aren't enough server nodes. So it's hard to operate a light client. If you More on the engineering side of things, anything I just talked about could be prototyped. Altair is on the way. We'll need light client prototypes. The light client itself has a relatively small footprint, so you could even try, working on a hackathon over the weekend and see where you get. Maybe you're like, hey, like that's super technical, but I'm just here. I'm super enthusiastic. What can I do? And I just say like run nodes, uh, especially nodes that have a minority of the network share, right? And this basically just leads to like a stronger networking layer, which is the foundation for like everything else. So it's very good for network health to do this. And yeah, thanks. If you want to talk to me more, please reach out on Twitter. There's a protocol R&D we have for research and development there. Also, a lot of this stuff is talked about on this ETH research forum. Thanks, everyone.